can a picture be created using mathematical lifeforms? That is what I am going to explain in this video. Cellular automata are grids of cells that evolve over time through purely local interactions. They were discovered in the 1940s at Los Alamos Laboratory through the work of John von Neumann and Stanislav Ulam. Later, in the 1970s, mathematician John Harton Conway designed the 2D cellular automation called Game of Life. The game is governed by 4 simple rules. Underpopulation. Any live cell with fewer than 2 live neighbors dies. Survival. Any live cell with 2 or 3 live neighbors lives on the next generation. Overpopulation. Any live cell with more than 3 live neighbors dies. Reproduction. Any dead cell with exactly 3 live neighbors becomes a live cell. When we run the game, we can create patterns that repeat, reach a static equilibrium, move infinitely across the grid, or instantly vanish. However, these 4 rules alone aren't enough for us. When we try to generate an image using only these rules, this is what happens. Meet ArcGen. She is the personification of the Arch Linux distribution. My goal is to reconstruct her using Cellular Automata. I will be using Python for this, and instead of walking through the entire codebase line by line, I will only explain the parts that matter. Before we can assemble ArcGen, we first need to write the code for Conway's Game of Life. We initialize our 2D grid and assign each cell an initial state of 0 or 1 with a 15% probability. Then, for every t plus 1 time step, meaning for every frame, if the cell value at that point on the grid is 0, we color it black. If it's 1, we color it white. Next, we need to count the active neighbors for every single cell. Instead of counting the neighbors around the cell one by one, which would be far too inefficient, we make the neighbors swap positions. Let's focus on the center cell and call it the home cell. Imagine there is another cell right next to it on the right, its neighbor. Rather than going door to door to visit every neighbor, wouldn't it be much easier to just invite the neighbors into our house? Of course it is. So that is exactly what we will do. We can invite the neighbor on our right into our house simply by shifting it to the left. And of course, since we are also a neighbor to the cell on our left, we shift to the left as well, moving the whole grid at once. If we repeat this process for all 8 surrounding directions, store each shifted state in a separate matrix, and sum them all together, we arrive at the total neighbor count for every single cell instantly. This process is called convolution, and the matrix that does this is called a kernel. After defining our kernel matrix, we run every cell on the grid through a logical path based on the rules of game using this matrix. Exporting this grid as a video with OpenCV gives us the output you see on the screen. Great, but if we try to generate ArcGen using only this code, we see the cells quickly dissolve into entropy. To prevent this, we need to modify the game. We have to transition from discrete cellular automata to continuous cellular automata. This means cells will no longer take binary integer values like 0 and 1. Instead, they will hold continuous floating point values. Again, we initialize the grid with random values, but the actual target state is held inside the target variable. As the kernel scans the grid, which is the convol 2D function handles, we no longer count discrete neighbors. Instead, we compute the total pixel density inside that 3 by 3 matrix and evaluate whether it crosses our threshold. This way, while life fails to emerge in dark areas, it thrives in high pixel density regions. The target force variable pulls the cell state closer to the original image's cell value by 12% per step. The density force value, on the other hand, evaluates all cells in the kernel except the center cell. If the neighboring density is below our threshold, it kills the cell. If it's above, it adds 4% vitality for the next state, boosting its value by 0.04. I know, it sounds a bit complex when explained out loud, but it makes total sense once you break down the math. Running this code gives us our lovely ArcGen, but she is currently deprived of emotion. color. Adding colors is actually quite simple. Instead of handling a grayscale single-channel matrix, we apply the convolution process across all three color channels. This time, instead of target force, I'm using target influence, which scales up over time as the frame count increases. In other words, as the video progresses, the probability of live cells forming the detailed structure of the image continuously goes up.